Hi, folks. Here we are again. We're in Chapter 7, Section 4. This is going to be about inverse functions today. And after this lesson, you should be able to determine numeric, algebraic, and geometric representations of a function and its inverse. So the first thing that we're going to look at here, as soon as I get this stuff out of the way, is what an inverse function is, and then we'll talk about, okay, what are the different representations that we might see. So first of all, our definition says that an ordered pair AB is in a relation if and only if BA is in its inverse. So if you look at what's happened here, it's really actually pretty straightforward. A and B are your x and y values. They get switched. So that's it. You switch your x and your y values, and there's your inverse function. So this is going to have ramifications when we're looking at a function itself, but when we're looking at a table, this is going to be awfully nice. So let's try this one together here. Let's find, here's a function, or just a function that I made up here with some data points, right? -2, 4, -1, 2, and so on. And we're going to write the inverse for this table. So I'm going to fill this in. So a little note here. When we want to talk about the inverse of a function, we write this notation here. It looks like it's an exponent, like it's f to the -1. That's an unfortunate coincidence. It's really saying f inverse. So let's see what we do here. There's our notation for inverse of f. Hold on a second. Let's see what's going on here. Okay, sorry about that. All kinds of crazy things are happening here with my PowerPoint here, and apparently it wants to kick me all the way back to the beginning of this slide. So pardon me as I catch up. Okay, here we go. So all we need to do here when we're talking about the inverse of a function, particularly in a table, is we just need to switch our x and y values. So up here where I had the point -2, 4, I'm just going to switch those. This is all I'm doing. So -1, 2 becomes 2, -1. 0, 0 is a nice one, isn't it? And then 1, -2 becomes -2, 1. And really, as far as the table goes, that's the end of the story. It couldn't be any nicer for us here. So let's see what happens when we have a function. So first of all, let's just talk about informally what's happening here. The inverse of a function is doing the opposite operations in reverse order from your original function. So let's see an original function here. I just made this up, y equals x squared minus 7. So when you look at this, if you're going to put a number in for x, what would you do? Well, hopefully you would square it first, right? And then you're going to subtract that 7. So the operations are you're going to square x, and then you're going to subtract 7. So we're going to do the inverse operations backwards. It's helpful if you start with the equation y equals x, so that way you actually have something to do, right? You have something to work with here. So instead of squaring x and then subtracting 7, I'm going to do the opposite operations, or the inverse operations, in reverse order. So I'm going to add 7 to x first. So I'm going to get the expression, or the equation, y equals x plus 7. And then after I add 7, then I'm going to square root. That's the inverse, that's the opposite operation of squaring both sides. So I'm going to add 7, and then I'm going to square root. So let's see what we actually accomplished here. So I'm going to bring back the idea of composition of functions to help me out here. So I'm going to pick a random number. I'm going to pick, let's say, 5 for x. So in my original function, when I put in 5, I'm going to get y equals 5 squared minus 7. And that's going to be 25 minus 7. That's going to be 18. So what I'm going to do is I'm going to take 18, and I'm going to put it into my inverse. And the whole idea with inverse functions is that they should unwrap, they should undo what was just done. So I should get back exactly what I started with, which was 5. So let's see if that happens here. So I'm going to do y of 18, and I'm going to do the square root of 18 plus 7. Well, 18 plus 7 is 25. The square root of 25 is, of course, 5. So yeah, we actually get back what we started with. And that really is the essence. That's the whole idea of inverses there. Okay, let's look at this a little more formally. So formally, this is what we do. To find an inverse, we're going to switch x and y, and then we're going to solve for y. So it's definitely a simple idea. Being able to actually solve for y is usually where, if we're going to have any hiccups, that's usually where it comes. But hopefully we're not really going to look at too many that are overly complicated for us to solve for y. Okay, so, and I made this a little extra difficult because we don't even have y in the problem. We have f of x. So we're going to make that little change right off the bat here. So we're going to find the inverse of f of x equals x cubed minus 4, and we're going to graph both functions. So I'm going to do this on my calculator, so you might want to have that handy. I have the picture for us here, so you don't have to, if you don't have your calculator, it's really not a big deal. Okay, so first thing I'm going to do is I'm going to switch my x and my y, and if you notice, I'm going to change f of x into y, so that when I switch it, it's really easier for me to work with. But anyways, I switched x and y, and now I'm going to unwrap this right here for y. So I'm going to add 4 to both sides. And then if you notice, I need to undo this cubing. So I'm going to cube root both sides. And when I cube root both sides, I get y equals the cube root of x plus 4. And again, I invite you to check this. I invite you to choose a number for x, plug it up in here, and then whatever you get out of that, plug that in here, and you should get back what you started with. It's a pretty neat little math trick, if you will. Anyway, so the way that we write the inverse of f of x, again, is f inverse. Again, this is, it looks like it's in the exponent spot, but we really read that f inverse. Or you can say the inverse of f at x is the cube root of x plus 4 in this case. But anyways, that's our notation. That's how we write that kind of thing. Okay, so here are my two graphs. Here's my cube root function, excuse me, my cubing function, f of x is x cubed minus 4. And here's my inverse, which is kind of going kind of, it's got this little sideways look to it. It looks like this. That's my cube root of x plus 4. So I had us graph this because there's something kind of, I guess, noticeable or maybe even interesting about this graph here. So can you see it? Well, I gotta erase this real quick. It reflects, doesn't it? Don't these two graphs reflect each other across this line right here? And now that I've drawn it in, you can kind of say, oh yeah, it kind of does, doesn't it? Well, that's actually a very special line. That is the line y equals x. So the question is, why did that reflect across that line? What did we do? Well, we switched all our x and our y values. We literally said let x equals y, so they could change places. So that let these graphs flip across the line y equals x like this. Okay, so what we're going to do at this point is we're going to look at some actual graphs. We're not going to look at the functions themselves, just the graphs, and we're going to draw the inverse on the same graph. Okay, so let's take a look at our first graph, this line here, and we're going to draw its inverse. So we're going to sketch the inverse. Okay, so I'm going to bring back the notion that we're just looking at, that this red line, in order to find the inverse, should reflect across this line y equals x. So if I sketch that in, well, I can see this point is going to just really kind of stay right where it was. This point here, it's going to kind of go through, and it's going to end up over here, right? And this point here, is going to go through and it's end up somewhere over here. And right, and with those 3 points, I get my line this way, right? I can kind of see that like that, or maybe it's not really easy to see, but maybe that's how you see it. Well, that's all well and good. That may not be easy to do necessarily. So I'm actually going to take another approach with this. Instead of trying to draw it like that, I'm gonna see if this will let me do this. Clear all this stuff out. I'm gonna actually plot this point by point. So this point out here, this is 4, 0. So remember what we said about the x and y values with inverses? They switch, right? So 4, 0 should become 0, 4. Well, 0, 4, as it turns out, was right where I was looking at before. So 0, 4 should be on my inverse. This point right there, well, that's 1, 1. Well, if I flip that, that stays at 1, 1. So actually, that point stays right where it is, doesn't it? And then lastly, I have, let's see, this looks like negative 2, 2. So then 2, negative 2 is right down there. That should be on my graph of my inverse. So and I know I've got a lot of stuff going every which way, but we have these 3 points here that are going to make up my line. And that's really good enough for me to get a sketch. And then when you look at it, hopefully you can see, yeah, that looks like it's reflecting pretty nicely across that line. Okay, let's look at another one. I'm going to draw a little half quadratic here, just that little side there. And we're going to do the same thing. We're going to sketch the inverse of this function. So again, I'm going to stick with the second thought that I had before of just plotting these points or getting these coordinates, right? 0, 0. This looks like negative 1, 1. This looks like negative 2, 4. And then plotting those points, those inverse points, excuse me. So when I take 0, 0 and I flip the x and y pairs, I get a point that's right down where it was. Okay, for my next order pair, I'm going to flip negative 1 and 1, and I'll get 1, negative 1. Well, that's going to go down there. And then I'm going to take and switch the x and y coordinates up here, and I'm going to get 4, negative 2. So let's see, 4, negative 2 is out here somewhere. And we can kind of then see how this is going to curve kind of like that. Which may not be really intuitive when you look at this at the begin with. But remember, it's going to reflect across this line. And if you draw that line in, I would actually even do it right at the beginning. And you kind of turn your head a little bit to the right. You can see that it's a pretty good reflection there across that line. Okay, so now we're going to move to, I'm going to give you guys a little practice here. So on your own, find this inverse. And you can pause any time along the way here. I'm just going to run through the steps in a pretty quick fashion here. Yeah, so why don't you go ahead and find this inverse. So remember what we did. We switched the x and y, and then we solved for y. So did you switch the x and y like this? And then I'm going to clear my fractions, multiply both sides by 7. And then I'm going to subtract 5. I'm going to divide by 2, and I'm going to get y by itself. And then I'm going to cap this off and just say that g inverse, or the inverse of g, is 7x minus 5 over 2. So anyways, again, just another little practice for you. We're going to move on to the next section at this point. Okay, so let's see a use for this. I do need to give you the warning of this is probably not nearly as exciting as some other topics. You're going to see inverses a bit more if you take pre-calculus. But anyways, we'll see at least a little example of this, and this is something we've actually seen before. We just didn't call it inverses. Okay, so anyways, the function here, I equals 10.5h plus 50. It's going to model Allison's income for a week, where I is the total income, h is the hours worked. So the first problem posed to you guys is to solve for h. This is going to be the inverse function for this model. So if I unwrap for h, too much. Well, I'll leave that up there, or maybe not. Okay, so if if I want to solve for h here, it's really nothing too nasty. I can subtract 50. And then I can divide by 10.5, and I can say my income minus 50 over 10.5. That's my equation solved for the number of hours. So if you think about this, if you have the number of hours worked, you probably want to put that into your equation for the income. And then if you took that value for the income and you put it back into here, you should get back the number of hours worked, right? I mean, that just hopefully makes some sense. So in that light, hopefully we see this function here really as the inverse of what we had up top. Okay, so let's say that Allison's total income is $533. How many hours did she work? So I apparently need to do a little more work here because my PowerPoint still keeps messing. All right, so as you might imagine, we have, with the $533 for income, I'm going to plug that into my, my variable for I. So I'm going to get the hours worked. It's going to be 533 minus 50. Divide all this by 10.5. And I get 46 hours out of this. And by the way, guess what you would get if you took 46 and you plugged it up in here into your income. You better get $533. Again, that's kind of the point. Okay, folks, big finale here. We're going to find the inverse of our parabola here, y equals x squared plus 2, and we're going to graph both relations. And this is going to lead to something that is, I guess, moderately interesting. So again, I'm going to do this somewhat quickly because we've already seen how to find these inverses. So I'm going to switch x and y. I'm going to solve for y. I just moved my y squared to the other side. I'm going to square root both sides. Notice how we get plus or minus the square root of x minus 2. So that's my inverse. No big surprises at this point. So when I go to graph these, here's my parabola. Right? I have my line of reflection there, and then here's my my two pieces, my plus and my minus, the square root of x minus 2. So if you notice here, my inverse, this piece right there, that's not a function, right? That does not pass the vertical line test. So is there something about the original function that can help us to determine if our inverse is going to be it's going to be a function itself? Well, as it turns out there is. I want you to take a look at it. And remember what we did. We switched our x's and y's. So everything that is vertical becomes horizontal. Everything that was horizontal becomes vertical. So before we had the horizontal line test. So that told us that our original function was or was not, excuse me, I messed that up. I have that backwards here. We never had the horizontal line test. That's the new one. We have the vertical line test. Nope, it wants to go, it wants to stay. Okay, I'm just going to reboot this here. We had the vertical line test before, and we know how that works. We pass a vertical line through the function. If it doesn't intersect the function more than once anywhere, if it intersects it twice or more times, then the original is not a function. Okay, so what we have with inverses is something called the horizontal line test. So the horizontal line test is we perform it on the original function, and if it intersects the original function or the original relation more than once in any particular horizontal line, then its inverse is not a function. Because look what would happen. This horizontal line here that I have in red would then become this vertical line over here. Essentially, we'd be doing the vertical line test on the second function, the inverse function. Okay, so let's look at one or two quick ones here, and we'll call it a day. So let's say that's our original function. Is the inverse going to be a function itself? Well, if I pass that horizontal line through that function, it's going to hit it more than once. So that inverse is not going to be a function. What about something like a line, like that? Well, yeah, we can pass all kinds of horizontal lines through this, right? And none of these are going to intersect that line more than once. So yeah, that's no problem. It's inverse. Whatever it looks like will indeed be a function. So here's one last one for you. Let's do something like that. So is that going to be a function? Excuse me. Is its inverse going to be a function or not? Well, again, we can pass a horizontal line, and it's going to hit that function more than once. So no, its inverse is not going to be a function. Okay, so I hope you enjoyed this lesson on inverses. You should be able to, at this point, determine numeric, algebraic, and geometric representations of functions and its inverse. And again, at the end there, we had that little bit with the horizontal line test. So hopefully you picked up on that as well. And have fun with the practice. I look forward to seeing you guys in class.